there are more and more satellites being sent into space. And we now have this, this big question is like, how are we going to manage all of the spacecraft and satellites that are increasingly entering orbit? So can you just set the scene with a little bit of explanation on what is this idea of space domain awareness, and just sort of what's the big picture there?
Yeah. So first of all, thanks for having me on your podcast. So as you said, there are more and more satellites that are being sent to space, but I just want to put it into context. So since I'll just give you some stats. So since the start of the dawn of the space age, since we Russians sent the Sputnik first satellite into space. Since then, we have sent about 10,000, 11,000 satellites. And, until 2 years ago, that was only, about 8,500. And now it is 10,000, 11,000. And that's because of Starlink, right? Just in the next decade. So that's in the span of, I don't know, a few decades, like, 6-7 decades, right? Now, in the next decade, we are planning to send on the order of 100,000 more satellites into space. So you can see the scale of the growth, right? It's a very sharp exponential growth in the number of space objects. Not only that, we are starting to have more and more capable tracking, infrastructure. More powerful radars, telescopes that can track during the daytime as well as nighttime. Radars can see smaller and smaller objects. And so suddenly we are going to see a lot more objects that we are going to be able to track, as well as, more satellites going into space. So that creates a kind of a scenario that quickly becomes not scalable, in a sense that the process that we have for the satellite operators to be able to fly safely and dodge these debris as well as each other quickly becomes not scalable with the manual process that we have. So that's really the key issue here. Really the commercial space industry is not set up to scale with the processes that we have.
Right. So, okay. So we have manual processes in place where human beings are sort of making sure that these satellites don't smash into each other, basically.
Yes, and you can quickly see that process isn't gonna, not be able to keep up with the expansion. And that is really one of the reasons that we are working on what we are doing, right? Basically automating that whole process at Kayhan Space. So just to give you a quick another set of stats. So since we have started our service, which has been about a little bit more than a year, we have sent out close to 300,000, actually over by now 300,000 conjunction notifications. And just to make sure the verbiage is correct. So when I say conjunction, meaning that it is a possible collision, it is not a collision, right? So collision is a binary thing. You either collide or not. But conjunction is a kind of a probabilistic event in space, right? So two objects get close to each other with their uncertainty bubbles, and then we say, okay, with the probability of such and such, they are going to collide. We have sent more than 300,000 conjunction alerts, and we have generated close to 1,000 avoidance maneuver plans. Now, if you consider having a human doing that, so take 2 hours per each avoidance maneuver generation. So you can see that the scale of the the problem that we are talking about across industry. And that's just across our own customers, right? So, if you take the whole the industry as a whole, the amount of time that is needed to adjudicate these, conjunctions and decide what you want to do will quickly get out of the hands of the operators.
Right. So another kind of a broader question I'm looking at here is sort of what are the major pieces in place that sort of need to exist to make this all happen? You mentioned ground-based, I think telescopes and radar detectors. It's a global it's a global effort. So can you put that global effort to make space safe, which of course you guys are intimately involved with, but even on the broad level, what are all the moving parts there? If we can start with sort of a broad look at the pieces needed. What exists now, and what is going to exist, if that makes sense.
Yeah. So, good question. And when we talk about space flight safety in general, and there are different terms that are used: space situational awareness versus space domain awareness. I mean, they each have a little bit different connotations or definitions, right? But in general, there are different segments that are kind of needed for us to be able to keep track of stuff in space and figure out where they are headed and, what are they up to? Or in the case of a debris, whether it's going to crash into something. Obviously, debris doesn't control itself. But in the case of another satellite that is probably from not such a friendly country, then what are they up to, right? Are they going to do something that they are going to threaten, some other satellite? So there are all sorts of those nuances that, when we are tracking these objects, we need to figure out. So there are different segments that are in place. And so I'll kind of explain what exists today and what is going to happen or needs to happen in the future. Awesome. So today, the majority, so the largest, and I'll put it in the context. So the largest network of radars and telescopes across the world that is currently 24/7 tracking space debris object is man-operated, owned and operated by the U.S. government. So it used to be managed by U.S. Air Force. Now it is Space Force. So it's called Space Surveillance Network, or SSN. So these radars, telescopes, they are managed by the Space Force, as I said, 18 Space Control Squadron. And they track on the order of close to 30,000 objects in space. And those are everything a little bit larger than 10 centimeter in diameter. So like bigger than Southpole in the LEO, in low Earth orbit, which is the space between about 250 up to 1,000 miles or kilometers above the Earth. Now, just to put that into context, and that's the largest catalog, about 30,000 objects. There are commercial radar systems such as Geolabs, commercial optical systems such as Numerica, Exanalytics. They track objects in different orbital regimes, but by far the largest catalog is maintained by the US government. Now, that is just a very, very small percentage of the stuff that is out there, because our models, NASA's estimate is on the order of 900,000 objects, big and small. And ESA's, European Space Agency's estimate is on the order of 1 million. So very close, big and small objects, right? So we are only seeing basically a tip of an iceberg, right? Now, so, but putting that aside, so that is the status quo right now. That you have certain ground systems that track stuff in space, and then the U.S. Space Force basically sends out emails to satellite operators that are flying in space today, anytime they come into conjunction with another object, right? And so you can kind of see the kind of the problem here, right? First of all, we don't see everything that we should see. So objects that are very small and tiny, they're okay, right? I mean, I don't think we are ever going to be able to track them reliably. Objects that are large, we are tracking them and we are able to hopefully avoid them. The problem is those objects we are not able to see them, but they are just big enough. So something in the range of, multiple millimeters to, several centimeters in diameter. Those are the objects that we are not able to track today. And those are the objects that are lethal. In other words, if they hit your spacecraft, they'll destroy it. And because, the orbital speed that we are talking about is, 17,500 miles an hour. So it's 10 times faster than the speed of a bullet. So imagine at that speed, something hits your satellite, it'll pierce through it. So, So basically, we have those, notifications that come from the U.S. Space Force in a form of an email to the operators, and that's it, right? And then after that, the operator needs to basically look at all those text messages. And remember, in the onset, I said that we have sent out close to 300,000 notifications. So imagine your mailbox, if you're an operator, satellite operator, depending which altitude you fly, some altitudes are more congested than the others. Then imagine that your mailbox is going to get filled, right, with those text messages, right, emails that is coming from the government. But then that just notifies you, okay, something is going to crash into you with this probability. Good luck, basically, right? So that's the status quo. What needs to happen is a couple of things. So there are really, I think, four major things need to happen. One is, as I said, we are not able to track majority of the objects that are lethal. So better tracking systems, both ground-based and space-based. And there are companies that are working in this area to be able to, track objects in space, up close with sensors, with sensitive sensors, and then be able to relay that information down to Earth, so we are able to add to the catalog. So better tracking, better algorithms. So being able to predict objects in space with better uncertainty, with better certainty, rather, right? So because especially when you are tracking a small debris object, you might have a very large uncertainty, several kilometers plus and minus. And so that doesn't give you a lot of information about where this object is, right? So that is another key piece. The other key piece is better processes. So I talked about, these emails and manual processes. So automation is key. Automation that is able to take into account all the realistic constraints, and based on those realistic constraints, basically recommend or tell you what you need to do in a case of a conjunction. That is, absolutely necessary, in my opinion. And then finally, really the better policies. So when it comes to space right now, it's kind of a wild west. So, there are certain rules that are set, and those are very minimal rules. Obviously, I'm not advocating to regulate the industry to death, but there are there are certain norms that needs to be set by international bodies to ensure that just like when you are flying in the you're flying an airplane, unless you are not airworthy, you are not allowed to take off, right? So similar rules and regulation needs to apply to a spacecraft. For instance, if you do not have a propulsion capability, meaning that if you cannot maneuver and change your trajectory, then probably you shouldn't go above certain altitude, for instance, above the International Space Station that houses the astronauts, right? So those are the things that are really four kind of factors or areas that needs attention.
Great. Okay, that's perfect. That's really nice to set the lay of the land there. It's perfect to get that from you as an expert on all this stuff, because it's not common knowledge. Where does Kayhan Space start to fit into that equation, and what piece are you bringing to the table? Because there's a lot that needs to be done. So let's start to double click there and see what's going on your side, and what piece of this are you taking on?
Good. Yeah, absolutely. Good question. So out of those four areas that I believe we need to look into, what the areas that we are focused on is two of them. One is, obviously automation that I'll go into, but the other one is more nuanced, is better algorithms. So, for instance, we are currently working with the US government, with the Air Force, to improve our atmospheric drag modeling. So, believe it or not, even when you are in orbit, you have atmosphere, very rare atmosphere, right? So, in a molecular level, right? You wouldn't feel when you are in orbit, you wouldn't feel the air hitting your face. If you are, obviously, you are able to be exposed in space. But there are, basically molecular atmosphere that actually hit object and slow them down. And so, they dissipate the energy. So, and atmospheric drag is the largest unknown force. That it's the largest force, and it's the most unknown in terms of prediction that affects the trajectory of these space objects. So, and that is one of the key areas that basically contributes to the large uncertainty of the space objects, of the trajectory of the space objects, right? So, especially when we track small objects, because of drag, a lot of times we don't know exactly where they are, right? So they could be here, or there could be 10 kilometers down the trajectory. So improving, algorithms, improving models, being able to more precisely predict where objects are going to be in few hours or few days from now is one of the key areas that we are focused on. So bringing down those uncertainties, that is very important. And the second area that we are heavily focused on is, as I said, autonomy. And by autonomy, what I mean is that obviously automating the whole process of getting the data from the ground systems, processing them at a scalable fashion, and then sending notifications such that it doesn't overwhelm the operators, because we don't want to basically overload the operators with unnecessary, junk information. We want to make sure that they pay attention to things that they have to pay attention, and ultimately being able to autonomously recommend course of action. And that is the key focus of Kayhan, where we have optimization algorithms that takes into account all the constraints from the operator. So whether it is your propulsion system, your physics-based constraints, right? So your propulsion system can fire in certain directions, cannot fire in other directions, or it can only generate up to a certain amount of thrust. But also real world constraints. For instance, I don't have a Sunday shift. I cannot perform maneuver during Sundays, right? As simple as that. So our algorithms take all that information into account and recommend courses of action that are feasible, and they are safe, meaning that we have checked that if you perform that maneuver and you perturb your trajectory based on that maneuver, you are not going to run into something else, right? So we do all that autonomously and recommend course of action to operators. So those are the two key areas that we are focused on.
Okay, so this is giving me a fuller picture. There's data that is feeding your algorithms. So who and what's the source of that data mostly? So what is the most useful data for you to make sure that these satellites are safe and that you're avoiding threats appropriately? And how do you access that? What's the state of the data input, if you will?
Yeah, good question. So as I said earlier, so the largest catalog, which is 30,000 some objects, that's maintained by the US government. So Space Surveillance Network is the system that is tracking. It's a ground system that tracks the objects. And those data are available to satellite operators, as well as companies like us that basically provide that service to operators. So we collect that data from the US Space Force via machine-to-machine interface via APIs. We essentially pull the data on every hour, and then make sure that we have the latest information about the catalog, right? So when I say catalog, it means that the whole population of the space objects and kind of knowing position, velocity, uncertainty. So basically knowing where they are and where they are going, right? But in addition to that, we also receive data from third-party data providers, commercial or other, European assets that track objects and collect those data, but also from operators themselves. So if you have an operational satellite, and majority of the satellites these days, they have GPS on board, right? So that GPS positioning information is very useful in terms of telling you where that object is exactly. Obviously, that doesn't help you with debris object because debris don't have GPS on board, but at least you will get a very good solution on your own satellite. So we collect all that data, and then it's our job to be able to, first of all, figure out which data is useful, which is not, and how we can fuse these together. Because many times, data from different sources can be actually contradictory to each other. So based on the information that we have from how reliable that data source is, we are able to make that determination and essentially rely on certain collection of data and basically generate our predictions. So essentially, our system is a cloud-based system that gets the data. If you can imagine that it's a process that collects the data, makes some determination, figures out where these objects are, propagates them forward in time, and essentially figures out who's going to hit with who, right? So,
right.
And we do that basically all the time.
Wow. Yeah. And I mean, it's worth kind of emphasizing the importance of that step. It's like there's tons and tons of data being produced. And this is a very kind of similar, it echoes some of the, challenges in the Earth observation space, which is people were really focused on at Ellipsis Drive. And it's like there's tons of data, but there needs to be insights generated, and it sounds like that's really a big piece of what you're doing for your clients. Because it's like the data itself is not enough, because it's actually there's so much data, and so it's about finding the action to take, which is a bigger step than one might initially think when it comes to just if you're looking at it from the onset.
That's correct. That is very similar scenario. I can see that. Yeah. Well, data is just it's a point in time, right? You need to kind of, first of all, be able to trust the source. And that trust will be generated by having enough information about how that data was collected, right? Whether you can trust that source of information or data or not. And then be able to then take that into and analyze it and be able to, exactly extract information out of it.
So who is, who's showing the most interest immediately, and let's talk a little bit about your clients and who's picking this up and sort of that should kind of give us a forecast too about like a little bit about where New Space is going, and just give people an idea, like, okay, so who are the companies like that you're serving? Like, why do we care? Who are they, and what do they do? So, because that's sort of the next step in this connecting this, bringing it down to earth, so to speak. So
So I'll answer your question in a kind of roundabout way, but I'll promise I'll answer your question.
Okay.
So basically, you said something interesting, that why do we need to care, right? So, and a lot of people might wonder, okay, why do we care if two pieces of space junk hit each other? Who cares? So let's put space in a context. So space is vast, right? It's unlimited as far as we know. However, the problem is that the lower Earth orbit, which is very narrow band, essentially above the Earth's surface, up to 1,000 kilometers, which is not very much. Think of it, Earth's radius is 6,300 some kilometers. So basically, we are talking about only a shell that is 1/6 of the Earth's radius higher than the surface. So very narrow band around the Earth. So that area is called lower Earth orbit, which the majority, 99% of the commercial space activity happens in that area. So it's in fact, a limited space. So let's put that aside. Space, the way we see it and the way everybody should see it, is infrastructure, just like our roads, just like our, our communication systems. Because take every modern technology that everyday person uses today in their life, and you can route it back to space. From air travel, your cell phone, communications, media, agriculture, food production, agriculture, modern agriculture, relies on the space, GPS, and even obviously national security and defense, right? So space is a limited infrastructure that supports our modern way of life. So we really depend on space, and we want this space to be safe, and we want that very limited area to be sustainable. So just like any other natural resource, we cannot just deplete it, and essentially, because once it is destroyed, it's actually harder than preserving other natural environments, right? So for instance, if you pollute the ocean, sure, it is difficult, but you can at least go and collect the garbage, right? In space, it is that much harder to go and clean it up. So that is why we need to care about space and whether space is sustainable or not. Now, going back to Kayhan and who we are working with today. So our immediate customers for our product, which is called Autonomous Satellite Conjunction Assessment and Collision Avoidance System or service. So satellite operators are our direct customers, obviously, right? So basically, if you are flying a satellite, whether one satellite or a constellation of thousands, that is a service that you would need to fly safely. Now, there are certain large operators, such as SpaceX, that has the enough resources and money and the manpower to put money and build a system for themselves, right? So SpaceX claims that they have an autonomous, collision avoidance system on their satellites, on their Starlinks, which is great for them, but not so great for everyone else that flies around them, right? So essentially, Kayhan Space is providing that service to everyone, every operator that might not have the resources of, say, SpaceX. Now, that is obviously our immediate customer, but as the commercial space industry grows, there are a lot of other areas that our services would be useful, right? So, for instance, one very immediate area or adjacent market is space insurance. So today, insurance brokers or space insurers, they do not have any certain models to really predict the risk of flying in space. The way they price their insurance premiums is based on financial models. Essentially, they are looking at the previous years and they're like, okay, I made this much money. Let's account for the inflation, and then I'm going to charge this much this year, right? So it's not really a risk-based model, which is crazy, right? Every other, insurance for every other industry is very meticulously, they study the risk, and based on the risk, they price your insurance, not in space. And the reason is that there are a lot of unknowns in this area, and there are a lot of the operators that simply don't have the capability to be able to react. So that is why the products that we provide not only can be used by the operators, but also say by the insurance insurers to be able to better quantify the risk, as well as better serve their customers and a more nuanced way, rather than just guessing some premium dollars and charging their customers. So there are other areas, obviously, satellite manufacturing, government, but those are the two immediate areas that I can think of.
We've gotten a lot of great stuff out of you, and so at this point, it's just bonus questions, I'd say. The one weird question I had was, if you have different satellites, do the algorithms, how many of your algorithms apply to general small sats, for example, or like how much does the algorithm need to be adjusted for a particular type of satellite? I'm just curious there, just like kind of an odd random curiosity there.
No, good question. And that is very important for us when we are designing our products and our algorithms, so that we can reuse them, right? Because we don't want to build a whole new algorithm for every customer. So in a sense, we build very generic algorithms that are suited for particular capabilities rather than the satellite itself. So there are different, for instance, propulsion systems, as I talked about. There are chemical propulsion systems that can be modeled a certain way. There are low thrust, electric propulsion systems that they generate very small amount of thrust, but in a very long period of time. So that's another model. And then there is, for instance, differential drag, that you change your attitude, but by changing that, you are able to impart force on your trajectory. So as long as we are able to cover those three models, we are fine, right? So it's really the idea of how you are able to take down the capabilities of a satellite or an operator, and bring it down to fundamental physics models, and then basically build the algorithms around that. And so that, then you can reuse that algorithm over and over again. So in that sense, it doesn't matter if we are providing a service to a CubeSat, which is this big, versus NASA's weather satellite, which can be, school bus size. The same physics applies. So, so we do make sure, and we do our best always to make sure that our algorithms are generic enough to be able to handle different cases.
Very cool. Well, I love where we took all that. I feel like I've learned about our industry, and I just think we shared a lot with the audience there, and I sure learned a lot. And I think others will too. So perfect. Like, thank you so much for coming on.
Absolutely. Yeah. Thanks for the interest and the time. It was great. Enjoyed it.